The core problem: traditional large language models, LLMs, are computationally inefficient because they recalculate common phrases, names, and patterns, e.g., New York City or Alexander the Great, from scratch every time they appear, rather than simply remembering them. The solution: Ngram. DeepSeek has introduced a memory-augmented architecture that utilizes a fast memory module for common word patterns, Ngrams. This allows the brain of the AI to focus on complex reasoning while the memory handles repetitive data. Technical mechanism: Ngram. Memory tables stores common word combinations in a giant, organized warehouse using a hash system for constant time, O1 lookup. Gating mechanism: a truth detector that assigns a value between 0 and 1 to determine if the retrieved memory fits the current context, preventing hallucinated memories. Expert versus memory balance. Research suggests an optimal ratio where roughly 20 to 25% of a model's spare capacity is dedicated to memory rather than active experts, MOE. Performance benchmarks: knowledge and reasoning. Significant jumps in MMLU, 60.4 versus 57.4, and reasoning tasks like ARC Challenge, 73.8 versus 70.1. Coding and math: improvements in human evil, 40.8, and GSM 8K at 60.6. Efficiency theory: Ngram allows models to reach useful data representations earlier in the network. Layer 5 of an Ngram model often aligns with Layer 12 of a standard model. Long context and efficiency. Context extension: dramatic improvements in needle in a haystack tests, 84.2% to 97.0%. Inference speed: memory can be offloaded to CPU with only a 2.8% throughput hit, making massive memory scales possible on consumer-grade hardware. For the past few years, the world of artificial intelligence has been obsessed with one very specific strategy: bigger is better. If you want a smarter AI, you give it more parameters, more training data, and a massive amount of compute. It's been the equivalent of building a bigger and bigger engine to go faster. But recently, we've started hitting a wall. These models are becoming so massive that running them is like trying to power an entire city just to get an answer to a basic question. It's expensive, it's slow, and it's fundamentally inefficient. While the industry tried to fix this with mixture of experts, a trick where the AI only uses parts of its brain at a time, DeepSeek just stepped onto the scene and suggested that everyone is still missing the point. They're arguing that even the most advanced AI models lack something every human has naturally: real, functional memory. Think about how you read a book. When you see a name like Alexander the Great, your brain doesn't stop to recalculate who that is from first principles. You don't have to think, okay, Alexander, ancient Greece, conqueror. Right, I know him. It's an instant automatic recognition. It's stored on a shelf in your mind, and you pull it down without effort. Current AI, however, is like a friend who acts like they're meeting a celebrity for the first time every single time you mention them. Even if they've seen the name millions of times during training, the model still spends a massive amount of energy rebuilding that identity internally. It's a repetitive waste of power because the internet is full of these locked patterns, phrases, locations, and common expressions that really shouldn't require heavy computation. This is where DeepSeek's new Ngram architecture comes into play. Instead of forcing the AI to crunch numbers for every single syllable, Ngram gives the model a dedicated fast access memory module. It's a complete shift in philosophy. The idea is to let the main brain stop wasting its time on the easy stuff so it can focus all its power on actual logic and reasoning. To make this work, the researchers looked back at a concept from the early days of linguistics called Ngrams. These are just common short word patterns, 2, 3, or 4 word combinations that show up everywhere. Phrases like United States, once upon a time, or the capital of are so predictable that they don't need a supercomputer to solve them. The way DeepSeek implemented this is actually quite brilliant. They built a shortcut memory table that works like a giant, perfectly organized warehouse. When the AI sees a familiar pattern, it doesn't have to search through a list. It uses a hash system to jump directly to the right shelf and grab the information it needs. In the tech world, they call this constant time lookup, which basically means that no matter how much memory you add to the system, it never gets slower to find what you're looking for. It's a level of organization that makes our current brute force AI models look incredibly disorganized. However, a memory system is only useful if it's accurate. If the AI just blindly grabbed whatever was on the shelf, it would start making mistakes. To solve this, DeepSeek added a truth detector, or a gating mechanism. Whenever the memory module suggests a piece of information, the main AI brain checks it against the current conversation. It asks, does this actually fit what we're talking about right now? If it's a match, the information is injected into the thought process. If it feels off or clashes with the context, the brain suppresses it. It's like having a personal assistant who whispers facts in your ear, but you're smart enough to ignore them if they're irrelevant. This ensures the memory supports the model without taking it over or causing it to hallucinate. When the researchers scaled this up, the results were nothing short of a pivot point for the industry. They trained this on a staggering 262 billion tokens, which is basically like stuffing a massive chunk of human civilization's digital history into the model. They discovered that there's a specific sweet spot for how much of an AI should be thinking versus remembering. If you give the model no memory, it wastes its life relearning simple phrases. If you give it too much memory, it loses its ability to handle deep, abstract logic. The experiments showed that the magic number is roughly 20 to 25%. About a quarter of the model's capacity should be dedicated to this fast access memory. The real-world benchmarks back this up in a big way. On standardized tests like the MMLU, which measures general knowledge, the Ngram models consistently outperformed standard architectures. But the real surprise wasn't just in knowledge retrieval, it was in pure reasoning. Tasks involving logic, math, and coding all saw a massive boost. This feels a bit counterintuitive at first. Why would a memory module help an AI solve a complex math problem or write a piece of code? DeepSeek explains that because the early layers of the model aren't exhausted by the boring work of reconstructing basic words and phrases, the model reaches its useful thinking state much faster. In fact, they found that the fifth layer of an Ngram model is often performing at the same level of complexity as the 12th layer of a traditional model. It's essentially giving the AI more depth without needing to add more physical layers.